We can't hear you, Prakash, if you're saying something.
Are you able to see my audio? Can you hear me?
Now we can. Thank you.
Okay, good. So I think I'm set. I think if I make you the host, the difficulty may arise. So just let me continue as is. Did you
Sounds
hear
good.
me? Yeah, okay. Hi everyone. Welcome to Learning Quantum Core for Applications. This is the sixth session. This is the fourth session. And this is organized by the Silicon Valley Quantum Computing, that is Silicon Valley Quantum Machine Learning Group and EOTF. Taposh is here. He is the what you call organizer of we call it SVQC, and I have joined him recently a month or two back, and I am part of the emerging OTF, and we work together in all ways to ensure that you can learn. So learning quantum core, initially we started with session 1 on classical versus the quantum, the history. Then second one, we went through the advantages, quantum advantages, math and science behind. Third one, we did some quantum exercises related to superposition, entanglement, and using Python Colab. And then fourth one, we are getting into now the quantum logic gates. Okay, let me see if I have anybody to enter. I'll once in a while just get into the to make sure that if anybody has to join, I admit them. So hope everybody has joined. There is nobody in the waiting room, correct? I don't see anybody. Okay. So let me move to the presentation now. This is quantum logic gates. So we said at the outset that the quantum qubit is at the core of this learning about quantum core, and it is surrounded by the computing, communication, sensing, and the algorithms at the and application at the top for doing the logic, quantum logic, gate logic, as well as the algorithms to implement on them and optimize them. So the computing, we in the earlier lessons we focused on the super positioning, and the infrastructure in itself is very complex. So we left it at the level of saying that there are physical uh, and for our expert, we do have in our here Ron, who is an expert in the hardware, and hopefully we'll be able to gain from him too. And the acceleration portion is very much like high performance computing through parallelism of superposition. Communication, as we said, was more to do with the uh, space and the time. How do we entangle and get the entangle across the channel with the Nyquist multi-level versus the Shannon's what you call the signal to noise ratio limitations, and that is the communication. And of course internet, quantum internet is another aspect of that. We will see whether we can even touch on it, but at least you be aware that there is something quantum internet which is part of the communication. On the sensing side, we said we have what you call the P, N, and T, which is positioning, navigation, and timing. So we have run some what you call the timing aspect of it, because that we did address through one of the, we do have weekly sessions, and one of those weekly sessions covered the clock. Because why quantum clock is important here in sensing is that it's able to replace the GPS, which is not there. So you can use the clock with very high accuracy and be able to manage. So that is why, and navigational, everybody knows about the navigation when you drive. So the position, navigation, and the timing, these are the PNT, we call it, of sensing, which is very important. We did cover something on the medical health also last time in the beginning. And then obviously today we are going to focus on the gates. Algorithms will follow and then finally end up with an application or something like that. So let me put the quantum logic, what we are going to do today, just to make sure that nobody is there to be admitted. Okay, I'll move on. So coming to the basic, we have quantum gates. We'll discuss some gates like a NOT gate, XOR gate, and then probably Hadamard gate, and end up with the IBM Qiskit, some references, etc. So to begin with, we have to understand what is quantum gates. So quantum gates generally are described using language of quantum computation. So which is obviously the electronic circuits which effectively make the circuit operate, which is at the different physical layers. That is, it could be at the millikelvin level in the conducting, there is superconducting quantum, we call it a CQ. So under a CQ, you will have millikelvin, and you will have the what you call um, the um, the subatomic particles which are being manipulated, and could be electron, could be photon, and we may be using laser, maybe using what you call magnetic um, the fields. So depending on whatever the logic is at the bottom, it needs to be manipulated using, could be microwave pulses or something, and then the pulses have to be programmed. So that means it's an analog domain. So essentially what we have is in the analog domain, what we need to uh, what you call, so the circuits are nothing but more combination of analog and some digital logic to control it. And the logics which are implemented in quantum are a little bit different from the normal classical. We'll come to that. But the idea here is whatever that logic is, it is going to rotate the unitary vector in the two-dimensional space. Last time we discussed about the vector space and the mathematics, which is matrix and vector space being used, because to realize it in a uh, lower dimension is easy. Lower dimension, when I mean, is 1 qubit and 2 qubits. It's possible to visualize through a uh, through some geometrical, or through some, what do you call the, we call it as Q sphere. But essentially that is easier, but as the complexity goes higher, it is difficult. So we tend to use the vector and the matrix notation. But at the same time, even though we use those matrix and all, at the end of it, we have to translate it to a circuit, and which happens to be a quantum circuit. So once we build the quantum circuit, the normal circuit, electronic gate circuits, are all electrical. You know, there is a wiring, you put the gates. It is very similar. However, there is difference is very much based on our multi-dimension. That is the Hilbert space, vector space, which we do, how we rotate the. So if you look at a circle with a with a unit circle with a arrow pointing from the uh, zero, there is a center, to the uh, circle, then that arrow is one vector. And if you rotate that, it is like a clock. If you have a clock and you rotate the analog clock, clockwise, anti-clockwise. That is what the rotation is. So you can think of these quantum gates enabling the rotation. However, the rotation, how it does it depends on what the algorithms are. At this time, we are not getting into algorithms. We say that we will be using that to rotate. The outcome is simply a unitary rotation and reversible. So like a clock, you can put a clockwise as well as anti-clockwise, and generally for our purposes we use pi radian is 180 degrees. So we normal, when you think of a pi by 2, that is perpendicularity, some vertical line and some horizontal line. You can call it xy, but don't confuse xy. Just keep it as straight. You have some vertical line and you have some horizontal line, and you have some clock, and you can move the what you call the unit vector in that clockwise, anti-clockwise, and within that all the play occurs, and then rest of them are either the image, like if you have a q1, q2, q3, q4, 4 quadrant, I can look at his image. Q2 is an image of Q1, etc., and so on and so forth. So the reversibility occurs because happens because we are able to. Our reversible is a requirement, and that is what the nature does it. And we are trying to address the nature. How do we represent that? So that's the idea. So idea here is we have some gates which may be in the higher order, lower order dimension of Hilbert space. That means you can have one qubit, which is obviously only two states, basis states, 0 and 1, ket 0, ket 1, which is what you call the spin up and spin down, and represented by an electron, and that could be in the low zero state or high state. And Ron, as you mentioned last time, corrected me, it's single electron for the hydrogen and multiple electrons for helium, like 2 electrons. So you can have a what you call the space, the vector space, and you can show the dimensions being 1 electron being 1 qubit, 2 electron being 2 qubit, but they may be in different states. They can be in ground state, or they can be in excited state, depending on energy level. So it is the energy transformation that is occurring by represented by the rotation. So electronic gates, when we talk about quantum gates, we have to understand that we are affecting the circuit which is rotating, and in that case we are energy is being imparted, and that energy is can be done in different way. Like we have got two. One is the gate quantum, other is the adiabatic. Adiabatic process means there is no transfer of heat, and that's the adiabatic process. So same way, energy level being constant without changing, because there are many energy levels, constant pressure, constant volume, etc., etc. So adiabatic is one process where the heat is maintained, or the temperature is maintained. So it's a part of thermodynamics, and this is where the gate quantum and the adiabatic quantum, the two differ. However, we can represent in gate quantum all the energy levels, and usually we try to use gate quantum for what you call the electronic based implementation. So I'll go on to classical computing gates. So if you consider single uh, bit gate, then we just connect the wires, as I said, essentially, and carry the information around the circuit. Now logic gate is what which performs the logic operation. This is Boolean operation. That is, if you have a NOT gate example, you can give a 0 as the input and you will get 1 as the output, binary. Okay. And fortunately for us, this is a reversible operation, because if you give a 0 and you get a 1, you give a 1, you get 0. That means whether you are going forward or backward, they are reversible operation. Now reversible operation is a requirement of quantum gates, not a requirement for classical gates. So if you look at the classical gates here, you've got a NOT and a AND. If you look at NOT, we saw that it is reversible, 0 to 1, 1 to 0. But if you look at an AND gate ABC, input 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Only 1 and 1 gives you 1. But what happens if you have 0 output? If I want to go from 0 backward, reversible, then I am not able to decide whether it is a 0, 0, 0, 1 or 1, 0. So it is not reversible. So there are classical gates which are reversible like NOT. There are other classical gates which are non-reversible. But for quantum, it's a requirement that gates have to be reversible. That's it. Let's look at some of the quantum gates. So the gates perform unitary operation. That is what we say. And what it does is the qubits, which we say represent some signal, and the signals flow from the circuit like in classical computer, the signal flow, whereas in the case of quantum, we do have pulses and all. So laser pulses, etc., or some trigger, which is what is used. It could be a step function or whatever the control functions that are used to effectively implement the quantum control logic. That's what we refer to as quantum gate. And they are represented by some kind of a function and some kind of a matrix. So even though the external pulses are applied in the physical qubits, at the top level, they happen to be some control. And usually we talk about the control system or the digital analog control system. And then with respect to the energy level, we talk about the Hamiltonian operator, etc. And they are also following the Schrödinger equation, which is the one for wave functions. So essentially, the quantum, as we said last time, that there is an approach, one which, because it's a particle wave combination, we have to understand that the last century, the Hamiltonian was one of the metrics are a statistical approach, and Heisenberger is the key player who formulated that, and Schrödinger was the one who formulated the wave equation. And even today, wave theory or wave functions which are used are easy to describe up to only 1 qubit. On 2 qubits and all, they get into much complexity, easier to handle through matrix and vector, and therefore we stick to the what we call Boltzmann approach, which is more of a statistical and Heisenberger approach, what we call. All was integrated by Paul Dirac, he brought it together. So we generally follow the what you call the bracket notation. So let me come to 1 qubit NOT gate. Let's define it. How do we define it? Now we don't say in terms of 0 and 1, rather we talk in terms of ket 0 and ket 1. So our input will be ket 0 and our output will be ket 1, and that will be represented. Oh, there is somebody in the waiting room. Let me enable the guy. Just a second. Admit. Okay. Shailesh will come. Okay, I'll move on now to what we were discussing. So what we have is 1 qubit NOT gate, and they are unitary gate, and they're represented as U generally. And so we say U naught. So U naught, the input is a ket 0 in the case of quantum, not the binary 0 as we say, it is a state. So the input state is a ket 0, and when you apply U naught to it, you get a ket 1. So it's nothing but you can represent in terms of electron being a spin up and a spin down. So you apply unitary NOT gate to, which is a quantum gate, and then you can get a, if you give a input 0, you get a 1, or if you put an input 1, you get a 0, and the U naught matrix is represented as 0, 1, 1, 0. Of course, I am talking row first and row first, row second, row 0, row 1, 0, 1, 1, 0. Some other people also go 0, 1, 1, 0 saying column wise, but I generally prefer to use row wise, and because it fits into the Python and arrays which we use, generally we try to do it row wise. So C2 is the complex space, and you know that we always represented the superposition as alpha ket 0 plus beta ket 1, which is represented as usually a psi. A psi is nothing but a Greek or Latin, I don't know which one, but psi is the term which is used to represent some of the linear combination of Ket0 and Ket1 with a coefficient alpha beta which are complex and they belongs to complex space 2. This is for one qubit. If you have multiple qubit, then it will go to C2. It's always tensor product. You remember that in quantum, any operation is always uh, um, tensor product. You never state it. You may use the x with a circle or you may not, but it is understood that it's a quantum tensor operation. And so one qubit is this. If you have multiple qubit, then you'll have to have multiple operation and they will become C2, C4, and then C8 and 2 to multiply, keep multiplying until you hit the 2 to the power n space, which is equivalent in terms of states. So focusing here more on the qubit state. So you got a U0, which is nothing but 0, 1, 1, 0. And this is a equivalent of last time we had seen a matrix called sigma x, polymetric sigma x, sigma y, sigma z. This is equivalent to sigma x. And so this is also called as X operation. Instead of U0, you can call it a X operation. So this is about one qubit gate. And so how do you verify that one qubit is operation, what we said it does? So that is where the Ket0 is represented by column 1, 0, and Ket1 is represented by column 0, 1. This is the standard which we said we will have to remember. And assuming that this is what it is, then how do you do the operation? So if you do a U0 multiply or not multiply the tensor operation with respect to a Ket0, this is equivalent to matrix multiplication in this case. And so we just replace Ket0 with 1, 0, which is the column matrix. And yeah, there is a new person coming on the waiting. So let me admit the person. Yeah, thank you, welcome. So we continue with our presentation here. So what we have is a one qubit not verify, and the verification is done through matrix multiplication, which is equivalent of a vector space tensor multiplication, in this case replacement, and that depends on the operation being scalar, vector, or only we are talking about magnitude here. So therefore it is a operation which is nothing but taking the matrix multiplied by the column vector specification of the Ket0, and then when you do so you get a Ket1. Same way you take a that is row column you can multiply, add and see that that's what it is. Same way with U0 1, in this case if you apply 0, 1, 1, 0, replace the vector that is the once spin down by the column vector 0, 1, you multiply 0 into 0 and 1 into 1, which is 1, and 1 into 0 and 0 into 1, 0. So you get a 1, 0 matrix, which is nothing but. So if you look at the alpha beta, U0 gate will swap the coefficient of the basis states. So what I meant is that if you have alpha 0 plus Ket beta 1, when you apply U0, it will become beta 0 plus alpha Ket1. That's what it is, swapping the coefficients, which is what is the verification of one qubit NOT gate. Now, the circuit, if you want to go, how will we have the circuit? So the circuit implementation, how to verify that is what is given here. You can replace the psi, which is what we said is our psi equal to alpha Ket0 plus beta Ket1. So you can say U0 you multiply by psi, and the psi being represented by vertically alpha beta. And so when you apply 0, 1, 1, 0 with alpha beta multiplication, it will get to beta alpha. So that means we said that we had alpha 0, alpha Ket0 plus beta Ket1. Now this has become beta Ket0, alpha Ket1. So U0 gate will swap the coefficients of the basis state. So that's how it is represented in electronically in circuit. So you got a Ket psi equal to alpha Ket0 plus beta Ket1. You apply X gate to it, and you transfer psi to phi, where the transformation of psi to phi has occurred with a swapping of the coefficient. So this is called as the what you call amplitude swap between the state 0 and 1. So this is the circuit, and this is how it is represented in what you call quantum. So we can have similarly two gates, 2-qubit gate, and we can have a tensor product of, instead of having one Q0 gate, we can have two Q0 gates, two NOT gates of quantum, and then have an operation on it, and you can see two X and Y operation. But in this case, they form a register, and when you form a register, you have to specify what is the MS bit and the LS bits, and therefore here the two are operating as a register where you got the MS bit is 1 qubit and LS bit is 1 qubit. And so you got, when you have a combination, you call it as alpha 00 plus beta 01 plus gamma 10 plus delta 11. Remember that this we did last time, saying that when you do a operation, a XOR operation, sorry, not XOR, the tensor operation, 00 01 10 11 are put together. So this is, you can either say ket 0, or you can say ket 00, or you can even replace by decimal 0, 1, 2, 3. Those are abstract, just the notation. Simple thing to notice, it's the alpha, beta, gamma, delta, which is the coefficient. And if we apply that to the two x's, we should get the result as delta 00 plus gamma 01 plus beta 01 plus alpha 11. So basically what has happened here is, you can see alpha, beta, gamma, delta 00. Here it is beta 01 has gone to beta 10, whereas alpha 00 gone to alpha 11, and delta has moved to here. So basically what here is, you have to see that the lower bit is assigned as MS bit. Okay, so what we have shown here, Q0, Q1, that's what we say to identify as the lower bit and the higher bit. So this is Q0, this is Q1. So there are two qubits, Q0, Q1, and when they are having that, and when you apply the operation, you get a combination thereof. We will see how it is like qubit A0. Here we are putting in terms of A0, B0, just to keep algebraic. So you can see here you are doing A0, ket 0, B0, ket 1, and this is the operation which is nothing but tensor operation. When you do A0, B0, A1, B1, you can see that A1, B1 is the least significant bit. So here this is the least significant bit, and this is the most significant bit. So let's verify how it works. So you can see here, if you have 2 qubit, you know that you are getting 2 U0 operations. So you just have to take 2 U0 operation and do a tensor operation. When you do a tensor operation on 2, the tensor operation is taken this way. So you take 0 and then multiply by this. Then you take 1, multiply by this. Then you take 1, multiply by this. And then 0, multiply by this. So this is the entire combination. So 0, 0. So when you do this operation, it turns out that the operation really swaps the alpha, beta, gamma, delta as delta, gamma, beta, alpha. So basically what has happened, alpha has gone down, beta has gone down, whereas this is gamma and delta, but they have not gone up as is, but they have flipped. So this is the one which is flipping. So you can see here, this is remaining as is, this is the one which has flipped. So 0, 1, 0, 0 and 1, 0, 0. In normal, what would have, here you can see. So this is the result of it. But originally we had 0, 1, 1, 0. So this is the result of it. So what we have to do is this reverses the order of the coefficients. That's all we have to say. Reverses, but at the same time, you can see it's not going alpha beta here, but alpha beta and delta gamma. So it reverses the order of the coefficient, and that's what is important here. And these operations are for 2 qubits, Q0, Q1, and same way you can see if the representation has 2 qubit is alpha 00, beta 01, gamma 01, and delta 11. So this is how the flipping occurs if it is 2 qubit as a register. So this is one of the operations, and similarly we can look at other gates. So the one of the more important gates is XOR or XOR gate, which we call in the classical. It is represented by C-NOT gate. C is control NOT. So what we saw here is a NOT gate 2 qubit, and we saw here 1 qubit. So 1 qubit gate being controlled is what is a XOR gate. So let's see how we get a controlled C-NOT gate expressed as UOR. So what we do is we say U XOR AB equals AA exclusive, sorry, this is your XOR B. So basically what it means is whatever is your MS bit and whatever is your LS bit, you are taking the LS bit. So when you apply on a AB, that is Q0, Q1, then you are getting Q0 as is with exclusive OR of B. So to be more specific, let's take the AB as 00011011. If A and B are either of them, so you can see here there is what is exclusive OR. In exclusive OR, we know that if you have 00, then you get a 0. But you get a 0, 1, then you get a 1. You get a 1, 0, then you get a 1. You get a 1, 1, you get a 0. Basically, that means what? In the truth table of classical XOR gate, if you have two bits being similar, then you get a 0. But when you have a 0, 1 or 1, 0, you get 1. So that's the classical gate of XOR. So same logic is being applied here. So you can see 0 or 0, exclude 0, 0 or 1, 1, 1 or 0, 1, 1, 1, 0. So this is the classical XOR operation. And so what we want to do is we want to take a Q0, Q1, 2 qubits and ensure that if the OR of the two is 1 and you exclude the 1-1 combination, that's what exclusive OR is, and you get the this formula, that is A or exclusive OR, in this case B is A comma A and B, which is equal to A and ARB. So basically we are trying to fit in the logic to make it a C-NOT operation. That's what it is. And this can be seen by applying the 2 qubit here. Like you have U XOR as some gate, let's call unitary XOR gate, which is C-NOT gate. So if you see the 000110 and if you apply using the formula which we stated here, A or tensor product with A exclusive or B, then you are getting the same thing here. So what we are doing is U00 you are taking and say this is equal to 0 or 0 or 0, and so exclusive OR of this. So when you get the exclusive OR of 000, 01, 1, 101 and 111, then what you are doing is you are doing a OR of the, sorry, you are taking the combination of thereof and then seeing that what the result comes out. So for a 00 we get 00, for a 1 which is 1, if you have a, so remember, whenever you have a 0 as the first bit, which is control bit, and if it doesn't, if it is a 0, then there is no change. So since there is no change, you are getting a 00, 01 as 01. But when the MS bit is a 1, it swaps the second bit. So the control bit changes the other one gets a NOT of it, which is what is control NOT. So control bit is the first bit, and the second bit is the one which is the target bit, and the target bit gets flipped. So here you get 0 becomes 1, 1 becomes 0. So this is what the flip is. So these two are the flip bits, these are not flipped, and so this is what the control NOT. So using the XOR, which is nothing but a classical gate, we are implementing a C-NOT. Therefore we call it either XOR, we call it C-NOT, but it's a control NOT. And from this you can see that the at first glance we can see LSB qubit remains unchanged. That means what? Of course the LSB is not to be changed, but if MSB is 0 and complements it to 1, so basically that means you know that this is the MS bit and LS bit. So depending on the control bit, it flips, and that's what it is. So this is a XOR C-NOT gate operation. Now we can also look through the matrix operation by using 2 qubit XOR gate. Here you got the combination. This is the only flip you can see. Normally it would have been diagonally 1 1 1, but you are getting a flip here. Since this is a 2 qubit gate for operating on a vector, the 4-dimensional C4 space, the matrix must be 4 by 4. Of course it is a 4 by 4 matrix. So you got the U XOR with this kind of thing, and when you use this matrix on individual 0 0 0 1 0 0 1 1 and all this, so this is being applied to 1 0. Ket 1 0 is a 2 qubit, and a U XOR is a 4 by 4 matrix. When you apply this, you can see that this basis, which is 1 0 1 0 is 0 0 1 0, so this is 1 0, and 1 0 gets flipped when you apply this multiplication as 1 1. So this is nothing but this is a C-NOT operation, or a exclusive OR C-NOT gate, what we call. So essentially the matrix multiplication, you know that if you have a 1 here, this is 0, then you are going to get 0. Only operation that can apply is when you have 1 1. So this is the one, and therefore this is the one getting flipped here. So this is a standard practice in quantum to follow the gate operation using the matrix to represent the same. And so output is determined by the rule. If A is 0, keep B unchanged. If A is 1, negate B, which is what we already apply a NOT to B. So B is the target, A is the what you call the control. So control bit versus the target bit, and that's what the operation is. So if you have for 1 0, we have A equal to 1, hence NOT is applied to result and becomes 1 1. Whereas 0 1, we have a 0, therefore there is no change. So it is 0 1. So basically the same thing being repeated in different ways, but essence is clear. There is one control bit, there is one target bit. The target bit gets a NOT based on the control bit being 1, and which is nothing, which is the same operation in classical as XOR, we said, and that's being achieved through C-NOT. So that's why it's called as XOR C-NOT gate. And the same thing can be shown. This is a different approach. You can see there the previous one alpha beta, we had the alpha beta and delta gamma reversed. Here we have got alpha beta same, only the gamma and delta are getting. So there is a difference between a 2 qubit NOT gate versus C-NOT gate. C-NOT is a representative of XOR, whereas NOT is a gate implementation of swap of the coefficients, entire basis vector being swapped. So this is again represented in terms of input outputs, in terms of MSB versus LSB. LSB is here, MSB is here. So this is what algebraically we are showing alpha beta. Algebraically because it is easy to show the complex parameters here being here. and how they are getting flipped or how they are getting inversion. This is the inversion on the target. So based on the input, and this is what it is. So A is the control, B is the target. So what it means is LSB gets flipped, whereas the control, depending on the control, that is A being 0, 1, and the LSB gets changed. So the same thing is represented in a different way. But we have to remember these are the two important gates, and the third most important in fact, the most important gate is Hadamard gate. So we saw the NOT gate, C-NOT gate, not C-NOT, not of quantum, C-NOT of quantum, or not uh, C-NOT. We are also saying XOR because classical XOR also meets the requirement, but it says control NOT. So NOT, C-NOT, and Hadamard are the three major gates. Now, why Hadamard gate? Very important thing on Hadamard gate is even here it's a 1 qubit gate. What it does, it causes the superposition of the state. So last time we discussed the state. Of course, I have to thank Ron for correcting me. One of the things I had observed previously was that when we call see, the basic challenge here is the representation. If you do a uh, what is it, Q sphere basis, then it is a XYZ projection. That means Euclidean coordinate, which is XY, is being projected on a XYZ, which is on a volume or a spherical volume in this case. So what happens is there the basis. What is the basis? Ultimately, any bit you have to measure. Any state you have to measure. And when you measure, how do you keep your appliance which is measuring? So in terms of qubit, Q sphere, we keep the gate vertical, magnetic, that is the electron detector or magnetic detector, whatever you use, that's kept as vertical. And then when you say vertical in the XYZ term, we call as Z basis. But that's not the correct interpretation. That is in the what you call Q sphere terms. But in the standard basis, what we use XY, or even not even XY, just the vertical and the horizontal mapping of X. So it's so we call it as standard basis to avoid the confusion. When we say Ket0, Ket1 is the basis, then it is standard basis. When it is example a Ket0, Ket plus or Ket minus basis, then we call it as alternate basis. Not the standard basis, because you can have many alternate bases. You can also have a basis of y, that is minus I and I. So the three major XYZ axes in block sphere are represented as +1, Ket0 and Ket1, and then Ket plus and Ket minus, and Ket I and Ket minus I. So the representation in those terms can be in the three different ways, but the standard basis is always Ket0, Ket1. So coming back to mapping based on Hadamard, what it does is if you give a input, a qubit, and let's say Hadamard gate, we apply basis vector Ket0, then you get a what you call the superposition of 0 and 1. So it turns out that because when you take a measurement, you remember you're vertically measuring it. That means you're or vertically are aligned with the axis, which is what, because appliances have to be measuring in a different way than what your what you call the vectors are. So in the vector space, because this is a virtual vector space, this is not the same as Euclidean. Even though we describe in Euclidean term, Euclidean is real, x and y. But in this case, this is not real, this is virtual. And the Hilbert space is what is used. And in Hilbert space, you have got complex coefficient which are not representable on xy coordinate, just plain xy. And therefore, you have got x plus iy, we call it, where I is the imaginary number. So the complex coefficient being x plus iy, they do have a different representation, and that is why we use the Hilbert space or vector space. And so if I give a ket0 as the input and then I apply the Hadamard gate, it gives me a superposition of 0 and 1, and they are 1 by root 2, because you remember the probability has to be sum to 1. So if you take a 1 by root 2 square, which is half. So half the probability is that it is 0 plus 1. Half the probability is it's 0 minus 1, ket0 minus ket1. So that's how you look upon the ket0 and ket1 mapping on a Hadamard. So you will get a, uh, this is, so there is a difference between probability density and the probability in itself. So alpha, beta, gamma, delta are not alpha square, beta square. They are alpha, beta, gamma because they are complex, and then when you square, you take the absolute value, you can get it to the real value. And that's why you say alpha square plus beta square equal to 1 for the probability, not alpha plus beta. So alpha, beta are indexes, are the probability distribution amplitudes or functions, but they themselves are the probability. Probability is derived by using squaring them and then adding to them depending upon how much is what is the matrix. And in this case, if you apply a Hadamard gate, it provides a equal superposition of two basis states. And so if you have 0 and 1, which is your basis states, this gives you a superposition of 0, 1 plus with minus, because there is a phase flip here. So we'll see how the Hadamard gate is, and here is the Hadamard representation of a matrix. Hadamard matrix is represented by 1 by root 2, 1, 1, 1 minus, minus 1. So when you take a Hadamard on a 0, you get 1 by root 2, 1, 1, 1 minus, minus 1 into 1, 0. 0 is represented by 1, 0, and when you multiply 1, 1 with this one, you get 1 by root 2, 1, 1. So this is the, that means what? Both 0 and 1 have equal probability, and that is why you are getting 1 by root 2, 0, 1. So we use Hadamard gate for converting input into superposition of state to be represented in the quantum gate. So you can say same way H1, if you take 1 by root 2, 1, 1 minus 1, you take a 0, 1 multiplication, you get a minus 1. So this is the flip. So that's why if this is the flip, this gets a minus. So superposition with 0 and ket0 and ket1 added and subtracted. So it's a additive and destructive as usual superposition as wave equation or wave theory, wave functions as we call them. And so that's all I have for the Hadamard gate. I have not represented them, but you can take a box and put a H in between instead of a X like we did in the case of uh, here. So if you put a H, of course this is 2 qubit, so you will, sorry, 2 state, so you have 0 and 1, and then the output will not be same. This is Hadamard, so you are getting 1 by root 2 here. So I have not presented that. Maybe I should add that. I'll add that later after the uh, presentation today. So before I come to the last stage, we have few more minutes left. I just want to go through IBM Qiskit. So IBM Qiskit last time we did not touch. It is the open source software development. We did collab, but we did not touch Qiskit. So Qiskit is a open source software development kit, and this is for developing quantum circuits. So it provides tools to create, manipulate quantum programs. So we can either use the composer, which allows us to compose, and or we can also do coding depending on what you use. There is a Python based implementation, so you can use the Python. Taposh, okay, waiting. Taposh is in the waiting room. Let me get him in. Sorry, yeah, hold on. So admit, yeah, welcome Taposh back. So we are almost at the end of the presentation. I'm coming to that. So the Qiskit is an open source software development kit, as we said, and it is uh, for developing the circuits. And there is a composer as well as code base. So you can do it without using any code, or you can do it through that is through the UI user interface development environment with the composer. But then it will translate into Quasm, which is a quantum assembly language, and Quasm 2.0 is standard currently. 3.0 is being proposed, and I hope that will get in as the standard, as every other vendor tries to adopt to the standard. It's still not standard 3.0, but 2.0 is standard. So it's still evolving, and this is Python based. And the quantum, what it does is the IBM Qiskit provides you a dashboard through which you manage your job. This is like our time sharing experience of the earlier days, when we used to submit the job and then wait for a day or two until we get the output. So you, good old days, people who used to use um, uh, cards or tapes, they will take a deck of card and submit, and the job will be submitted, and the job will come back. You go overnight, you work in the night, come back in the morning, and next day or somewhere your deck will be there, and then you can reinterpret it. So very similar, but this is cloud based. So we are fortunate today to have cloud based. So all you do is you write a Qiskit program, or you compose a program and queue it, and you send it to the runtime, and runtime manager either gives it to a, quantum data center, or it may just be a simulator. Based on the simulator or on the data center which it is operating on, it will run and execute the kernel, and then you will get the after the hardware returns the answer or whatever the problem you addressing. Usually we are talking about circuit here, so the circuit may be required optimization and all. Those will leave at this time. Important is functionally you should be able to implement a. So how do I? Next question is, how do I get a Qiskit? So here are the links to the Qiskit. You can use it cloud based, or you can use it on a local system, and the runtime is what is the necessary portion which you have to. If you are using a Jupyter notebook, or you are using Anaconda to install on your local machine, then you can use various IDEs, or the uh, development environment, or integrated development environment as they are called, depending on your OS, whether it's a Mac OS or Linux, Windows. But ensure that you have a Python 3.7 or higher. 2 dot is almost scrapped out now most of the places, but you should use Python 3.7 at least minimum, and then you can install based on if you are using uh, Python or something, you can pip install the Qiskit and IBM runtime which is required. Create your own profile if you are going to www.ibm.com, and you can use that. And there are of course you have to run some application code, so either you can run it on the simulator, or what you call IBM Q provider they call it, and these are all based on the API. So when you go to the cloud, you will be able to get an API token based on your registration, and that you have to plug into your configuration, so that you can use the API key to mm, get the operation done. And that's what we have here. And I think I'm going to end here. We are at the almost fag end of it, 10:58 now, 2 minutes. So what I have to tell you is that we use some reference book, and I did include that last time. Once Ron mentioned, we are not given any uh, uh, formal book. However, I can tell you that we do bring, because everybody may not be having the funds to buy the book or something, even though it is low priced, around $15 to $20, I believe, under $20. But if you cannot, definitely use the other references we have given, and that include the that I will include that it's not here, but you can use the Qiskit documentation tutorial to go through, because that is one thing which is very important for the circuit. Of course, there are other kits available from manufacturers, but IBM tutorial, because they are the ones who are contributing more to standard, I would recommend that you use this documentation which is there in the link. And with that, I think I'm going to also use their glossary, because they have contributed the glossary to what the quantum terminology is, and half the battle is won if you understand the glossary. So because you will hear the term called oracle. What is that oracle? It's a black box. Then you got ansatz. What is that? That's an what you call approach or an attempt to assumption about an unknown function. So if you have unknown function, then it's a ansatz. So you are trying to assume that it could be this. So that is same way wave function. What is wave function? Is it wave? Is it function? It's neither wave nor function, but it's a formal a formal way of representing the wave function as a function of quantum qubit. And so there are many things which you will come across glossary. So with that, I will close the session for the day and open it for Q&A. And if you have any questions, please ask now. Otherwise, I will try to um, wrap up these sessions and provide you the links. It may be that there are some YouTube learning application, and so I may be replacing them because some mistakes I would have made. I acknowledge my mistakes and will correct them. So if you find something replaced, please bear with me because I am reviewing each one of them, that there is no mistake in that, and that may take some time. So that is why I am a little bit worried that I do not want to give a wrong idea to people, because if you have a firm, correct approach, then only you will succeed. So hopefully that's what my and our effort from Taposh, myself, Professor Gokhale, and whoever is Ron actually has been very helpful. So all those people who are there uh, today, whatever is there in the quantum core for applications, if I replace them, I will let you know that there is a new version. Okay, that's all. So I will stop sharing and ask questions before I can close the session. Go ahead. Anybody? Any questions?
Just one thing, not a question. I put the link for the book, the Amazon book you had referred before, from Introduction to Quantum Computing, Layperson to Programmer.
Correct. Okay, got
Also,
it.
if that's expensive, there is free videos on YouTube
Correct.
by the same professor, and his slides are also available. I'll get the link for his slides from GitHub.
Super, super. So this is our San Jose professor, right?
Yes, that's correct.
Yeah.
That's correct.
Okay. Okay. Yeah. Yeah. He's he actually is a the author of this book. He's detailed. Of course, sometimes the complexity you lose the common approach to getting things done faster, because there are too many volumes, 20, 30 chapters. It's very hard to follow some of the portions, especially early portions, but definitely it's one of the best books we have. Yeah. Any another message? Any
No, that's
message?
that's the link to his GitHub with all the PowerPoint slides there as well.
Yeah. Yeah. Basically, we do follow that book, but we are not following to the 100% extent of it, because the one of the main reasons is the some books use Qsphere, whereas he has shunned it very much all the way, and it's a difficult which one to address first. So the problem with the subject is what comes first and what comes next. And some of the orders are very subjective. If I go to Wazirani, or if I go to what you call the Saskin, these are the Susskind and all. These are all Stanford and Berkeley professors of yesterday's, who were his professors. Now their approach has been a bit different. His approach is different, and our approach is going to be subjective.
Right. Yeah.
So
No,
please
that's true.
pardon us for that, because we are trying to gather from all the places.
Yeah.
If there is
I mean, it will be great if we can get one of these days Dr. Bazirani just come here and talk to us as well.
Sure. I'll put a word to him. Let's see if we can
Yeah.
get him,
Yeah.
because it is all their timing, right?
Timing is an issue. Yeah, but we can book ahead of time. Yeah.
Correct. correct. We will do that.
This
Okay,
is
so I will stop the recording here. Where is stop recording? My gosh. I am more. Stop recording. Yeah, okay.